So is it visible? The video is visible? The slides are visible?
They are visible.
Yes. Okay. So, I'm here, Kavita Midkari, to present a seminar on microwave remote sensing in the Antarctic mission. I'm working in Microwave Techniques Development Division Group at Space Application Center. So, to begin with, I'll first introduce you with the cryosphere term. Basically, cryosphere is related to all the cold regions, the science related to cold regions. And
Ma'am,
yes,
hello.
yes, yes,
Ma'am,
ma'am.
can you please put your screen on the full screen mode?
Yeah,
Skype.
sure. I think now it's fine.
Fine now.
So cryosphere is basically related to the science of cold regions. As you can see, cryos is cold or icy. So these portions of Earth's surface where water is in the solid form. So various forms can be seasonal snow, sea ice, or ice sheets, glaciers. We all know about this, right? Then ice shelves, then glaciers, then lake ice, then frozen lands. Okay, so why we are studying this cryosphere regions is first and foremost thing is its importance due to the climate change. It has a very drastic impact on the climate change. Then the meltwater goes to the sea level and it rises the sea level, so it is very dangerous for the people living in the surroundings. Then so that's where we study the cryospheric regions. So in these regions, though Himalayas is also one of the parts, but in this seminar we'll be considering specifically the polar regions. So polar regions consist of two regions, that is the Arctic and the Antarctic. We all know about this, that Arctic lies in the North Pole and the Antarctic lies in the South Pole. But what is the basic difference between the Arctic and the Antarctic regions is Arctic is a cold ocean, all right? So it is basically ocean surrounded by glaciers, snow, ice, and also the ice covering the Greenland. But if you see Antarctic, it is basically icy continent. It is a landmass surrounded by the ocean. So you'll see the ice shelves and the icebergs floating in the ocean. Then the most important thing here is like the exploration of Antarctic started a long back by Captain James Cook, and he started this in 1773. So you can see how, like from 70s, we are studying the Antarctic regions, and we are exploring and monitoring those regions. Later on, like why we are studying. The importance is because these glaciers, the Antarctic glaciers, the Antarctic calving, all these things are responsible for climate change, and that's why we go for studying those regions. Then, as you can see that Antarctic is a continent, but it is divided into three parts, which is Antarctic Peninsula, West Antarctic, and East Antarctic. So, Antarctic Peninsula has a large, or you can say widespread glacier retreat, and it moves to the south. Then West Antarctica is it is overall, you can say, the studies say that it is overall shrinking, and it constitutes 20% of the Antarctic region. Then East Antarctic is basically contributing large amounts of meltwater to the global sea, and it constitutes 76% of the Antarctic region. So as I said earlier, you can see in this right-hand diagram that Antarctic is a landmass, and it is surrounded by the sea ice and the ice shelves and the ice sheets. All right. So basically, I'll tell you one important thing here is like this sea ice portion in the white color you can see, right? So this portion is it plays a very important role in a way, like people who go for expeditions they need the sea ice advisory, and for that purpose we find out the sea ice types. We classify the sea ice types and we find the sea ice concentration as well. So what it is basically we'll see in the later part, but this portion plays a very important role for the people who go for the expedition. Then, how the sea ice forms, as I said, that the Antarctica is a landmass surrounded by sea ice and ice shelves and other things. So, sea ice basically forms from the cooling of the ocean. All right, so it forms on the ocean surface, and why it happens? Because of the supercooling of the uppermost layer. Also plays an important role when we study the Antarctic regions. For example, like I'll show you some images. So this is there are basically different types of there are different ice types, and those have importance because the growth process of sea ice depends on those formations. So you can see first if the ocean is rough, all right. If the ocean is rough, then the fragile ice, this is kind of ice you can say, a very smooth ice, it converts into pancake ice. Then due to the rafting and dredging, this pancake ice converts into rafted pancake ice, and then due to cementing and consolidation, this pancake ice may convert into the cemented pancake ice. And later on, this formation grows into a sheet ice. So this will be a newly formed sheet of ice. And later on, with the seasonal variations, this newly formed sea ice grows into first year ice, then multi-year ice, and so on. Then second is if the ocean is calm, then the fragile ice goes into grease ice, and it is very smooth. So this grease ice converts into nelas. So basically, nelas is a very thin layer of ice, and this, due to the rafting process, gets converted into the rafted pancake ice, and later on, due to the congelation of the ice surface, it converts into sheet ice. So this is the sea ice growth process. So I'll show you some images of all these sea ice types. You can see this fragile ice. So this is the first step. All right. So this forms near the edges of the ice. So you can see it's very smooth, and this fragile ice gets basically what we call as the movement of the winds. This fragile ice gets converted into rafted pancake ice. So you can see how this pancake ice looks like. It really looks like pancake, right? Then this is one another formation. Basically, there are various features. There are apart from pancake ice, there are ice floes as well. So floes are nothing but formed due to rafting process only, but later on they get converted into ice sheet. Now this pancake ice, you can see this is little different from the rafted pancake ice. It has some raised edges. So this is like cemented pancake ice, and then I discussed earlier, right, that if the ocean is calm, then the grease ice, it will be really like a grease, all right. So this gets converted into nelas. So you can see in this diagram, in this figure, that it is a very thin layer of ice formation, and the ocean is clearly visible below that. All right. So this type of ice also creates a problem while we classify the sea ice types. And also, if it has a similar properties, the ocean, obviously you can see, so it will it will also create a problem during classification of sea ice from the open ocean. Right. Then this is the new shiite formation, and this later on due to seasonal variations, it will during winter and summer. In winter, it will get converted into get accumulated, and it will get converted into first year ice. If this first year ice gets accumulated for one more year, then it converts into multi-year ice. So these are the various types of formation. As I said, first year ice and multi-year ice. You can see that in this multi-year ice, it is really rich multi-year ice. It is not very smooth one. Then fast ice is nothing to do with the formation, but it is actually the landmass portion, which is the ice portion, which is attached or clinched to the land. So this basically, if we go for optical remote sensing to classify all the sea ice types, then this fast ice creates a problem because, as you can see, this has it really looks like a sea ice, but it is actually not a sea ice. It is a fast ice, and it will usually have snow over its surface. Then there are some other features also, like leads and polynyas. So what are these features? Is leads basically are formed during the melting, and these are small, you can say, water channels. So these features, really help to the voyagers or to the navigators and the people who go for expeditions. Usually the ships travel through this leads only. So when we form a sea ice advisory map, we usually consider these for classification. Then polynyas. Polynyas are similar to leads only, but this is like little bit exposed ocean, and it has a larger area compared to the leads. So leads will be more of a linear features, but polynya will be more of polygon types. So what are the parameters that are very important in, you can say, I would not specifically say Antarctic, but in the polar regions overall. So basically for offshore operations, as I said, so the sea ice extent, then the sea ice types, then the sea ice thickness, then the sea ice drift velocity, then the internal stress, and other properties such as air temperature, atmospheric pressure, wind velocity, then the current velocity at the time of the navigation. All these parameters are very important, and not only one factor will play an important role while we form a sea ice advisory, but a combination of all these factors is very important. Then climate. So in climate, climate change, the sea ice extent and the sea ice thickness are the important parameters. Then albedo, insulation, latent heat export, then surface stress, and then ocean mixed layer. So all these are the areas of interest, and their pertinent ice parameters. I will not go into the depth of this. So we'll see some examples. So basically, why we go for remote sensing in polar regions is obvious, because of the obvious reasons that those are very inaccessible, and the regions are cold for most of the year. So that's why we go for remote sensing technology. So as said by Campbell and Goodmanson, they have written Physics of Glaciers book as well. These two people, they are very renowned, and they have said that it is both difficult and expensive also to conduct surface investigations in icebound areas such as the Arctic and Antarctic. These regions are in effect surrounded by what we call as observational barriers. Alright. So in order to penetrate or to look into these observational barriers, it is very necessary to acquire synoptic or large-scale view from satellite platforms on a repetitive basis. So So why we are not discussing here visible and infrared sensors is also due to the fact that in polar regions it is dark for half of the year and is often cloud covered. So visible and infrared sensors or optical sensors are not very effective for you can say long-term monitoring and operational purposes. So that's why we usually have active and passive microwave systems, which are proven to be reliable for sea ice monitoring. So, so what are the techniques that we use in remote sensing for monitoring of this polar regions? Is you can see we use passive microwave radiometers. Alright, then we have what are the parameters that we are deriving from passive microwave radiometers is the you can see ice distribution, then advanced and retreat motion, or you can see the velocity and the ice depths and albedo. So then active microwave remote sensings, we have SAR. So we usually derive sea ice concentrations, then the roughness and the drift from the SAR images. Then we have altimeter. So altimeter usually is we derive the topography and the motion and the elevation change, and the sea ice topography roughness, etc. So these are this is the overview of what are the parameters that we can derive from the different remote sensing, or you can see the microwave systems. Then, I don't know whether I should talk about passive microwave remote sensing or not, but a little bit I'll cover here. So basically, objects on the Earth's surface, they not only emit the infrared radiation, but they also emit the microwaves at relatively lower energy. So when sensor detects microwave radiation naturally emitted by the Earth, the radiation is called as passive microwave. I think we all know about this, so I'll just quickly go through this. So clouds basically do not emit much of the microwave radiation compared to sea ice, and that is why microwaves are used or are found to be useful to detect, or you can say separate the sea ice from the clouds. Then microwave emission is not only tied to the temperature of an object, just like infrared, but it also depends on the object's physical properties, like you can say atomic composition and crystalline structure. So if we see the sea ice, then the crystalline structure of ice typically emits more microwave energy than the liquid water in the ocean. Thus, those microwave sensors can detect or distinguish sea ice from the ocean effectively. Now, the major drawback of passive microwave radiation is it's quite low energy, and what happens is that as a result, the radiation has to be collected over a large region. So the FOV, the field of view of collecting the data, will be much larger, and that's why the footprint that we'll be getting, it will be of a larger area. So that's why we won't be able to detect the smaller features such as the leaves that I described or the icebergs, So it becomes very difficult. So that's why in such cases we do go for you can say passive microwave, but rather we go for high resolution SAR images. So sea ice observations using passive microwave sensors began in early 1972, and different passive microwave sensors later on came, and they are still in various products are being derived from all these passive microwave sensors. Like for example, JEXA has AMSRE and AMSR2 missions, and all these products are available on NSIDC website. The data products derived from ESMR, SMMR, SSMI, and MSRE and MSR2. So the products will range from like you can say sea ice thickness to sea ice concentration, etc. So a hell lot of products are available for Antarctic as well as Arctic regions. Then and also like most of the studies are being concentrated on passive microwave only in case of polar regions only. Then one few examples I'll be considering. Okay, fine. So the scientific basis of sea ice microwave remote sensing we'll be discussing. So you can see that there's this graph, the microwave emissivity versus frequencies. So how the frequencies versus the emissivity is able to distinguish between the different sea ice types, like the first year ice, the multi-year ice, the open ocean, and also we need to consider the dielectric properties as well. So the change in dielectric properties strongly influences the radar basket rods, hence gives typical signature during seasonal cycle from melting to freezing. So at SAC Ahmedabad, people have done used passive microwave data SSMI to map the sea ice features like sea ice and open water and ice sheet. And how they did is the basic procedure is like the different frequencies have been stacked in one RGB, and visually they have interpreted and saw the spectral profiles of sea ice, open water, and ice sheet. So we can see that it is clearly distinguishable. The sea ice is clearly distinguishable from the open water. Then people have also used the polarization ratio and spectral gradients for sea ice classification, you can say. And one of the algorithms that is there are other algorithms also using passive microwave data. But one of the algorithms I'll be discussing as an example is the one proposed by Cavalry in 1994. And what he did is he derived two parameters, that is polarization ratio and spectral gradient. So the frequencies that he used was 18.7 gigahertz and 36.5 megahertz. So you can see in this scatter plot that how the polarization ratio and spectral gradient is effectively, differentiating between the first year ice, the multi-year ice, and the open water. So now, why we are discussing all these sea ice types? It is not just the sea ice types, but once we are able to distinguish between the different sea ice features, specifically the sea ice and the open water, we can derive the sea ice concentration maps. So, what the sea ice concentration is, I have to switch to some slides, so let me go to that. So you can see that, this is the upper image. This is a Sentinel-1 processed image, and I have marked some portions. That this yellow portion is a land mass. Then you can see the purple portion is the sea ice, and the completely bluish or black portion is the ocean. So we have to distinguish between the sea ice and the ocean. Once we get the polar ice features map using some other technique, we get the sea ice concentration. How to derive the sea ice concentration is, now you can see this ocean and this is sea ice. Okay, so for example, I'll consider a small portion of you can say a 9 by, this is a 9 by 9 matrix of the polar ice cover map, depicting what the three classes. So one is representing the land ice, two is representing the sea ice, and three is representing the ocean. So we'll just see that in this green box there are as an example, we are taking a 2x2 window. Okay, so what we are doing is we are moving a 2x2 window on this polarized features map, and what it will do is it will count in this 2x2 window how many pixels are there of the sea ice. So you can see that in this portion, this 2 represents the sea ice. So out of 4, it is representing 2 pixels of sea ice. So the sea ice concentration will be 2 divided by 4 into 100, which is 50%. So this 2 by 2 matrix will get projected to a 1 by 1 matrix having a 50% sea ice concentration. So this is how we derive the sea ice concentration, and what it defines is basically how you say that if the concentration of the sea ice is more, you can say as with the increase in the sea ice concentration, it becomes really difficult to break the ice using the ships. All right. So the ships can't, if we are not able to break the this ice walls or with high sea ice concentration, then the ships won't be able to move or proceed further through the leads. And therefore, we have to find out the sea ice concentration, and it is one of the major parameters for you can say generating the navigation maps. There are other factors also, but it is one of the major parameters. Then we have active microwave remote sensing, and so basically satellite sensors can also actively emit microwaves toward the Earth's surface, and of remote sensing we call it as active microwave remote sensing or radar. So this same technology is being used to track aircraft, ships, and speeding automobiles. There are 3 types of active microwave sensors, which are imaging radar, non-imaging radar, and altimetry. So we'll see one by one what all of this define. So first of all, imaging radar is similar to a photograph taken by camera, but the image is of radar waves and not visible light. So sea ice, which typically reflects more of the radar energy emitted by the sensor than the surrounding ocean, it makes easy to distinguish between the two. But what happens is the amount and the character of the reflected energy are the functions of the sea ice physical properties, and which are very complex. So it is very difficult to interpret the radar images of sea ice. Then imaging radar, one of the examples of imaging radar is the SAR, synthetic aperture radar. In using SAR instruments, we can detect small features as well, like leaves and icebergs, and other small features like exposed rocks and etc. So this fine resolution, allows to analyze the sea ice and help route ships through ice-covered regions, and it is particularly valuable for operational ice sectors. Then we have non-imaging radar. So non-imaging radar, best example is of scatterometer, measures the amount of reflected energy or backscatter from the Earth's surface, and it cannot obtain the same amount of detail as the SAR sensor, but obviously it can provide a complete or daily data about sea ice day and night through cloud cover. Then so altimetry, basically it has little, you can say a similar principle, not completely similar. It basically sends a pulse of radar energy towards the Earth and measures the time it takes to return to the altimeter. So the pulse round trip time, it determines how far the satellite is from the reflecting surface. Then, when compared with the known reference, this information is used to make attitude of various features at the Earth's surface. So, what are the parameters that we can derive from altimetry? These are like the height of the sea ice surface above sea level, then the thickness also we can derive from the altimetry. The one of the altimeter that is developed by ISRO in collaboration with the France Space Agency is the Sterile Altica. It is the satellite for Argos and Altica. It is called a Sterile Altica, and it operates in single frequency band, that is the Ka band. And it was basically launched dedicatedly for ocean observations. So, okay. So, one example I'll be sharing here is of monitoring of ice shelves using scatterometer data. This is of SCATSat 1 and OSCAT. So, you can see that this is an Ameri ice shelf, and it is one of the fastest you can calving ice shelves. Recently, also in February, some portion of the ice shelf calved, and it is still floating. The iceberg is still floating, and we are monitoring how these icebergs are. We are monitoring the iceberg calving events as well. So here the two examples, these are of we have monitored the ice shelves using SCATSat and OSCAT. So the study was done in 2010 and 13, and you can see how the red to violet indicates the warm condition, and how because of this the ice calving events must have happened. And the major event that was ice calving event happened was in 2017. It was for Larsen ice shelf calving. Then, so we have also used the RISAT star data for evaluating the CI signatures. So you can see that this particular portion, this is a RISAT image of December 2012. This is a Bharati station. This is a Bharati Indian Research Station, and we have to reach from the here near this portion, and for this purpose we formed the sea ice route. So basically, for that we study the various signatures of sea ice. Then we have ice deformation also. Then also icebergs also we study. Then crevasses also. There are crevasses in some portion of not bigger ones, but the smaller crevasses are very visible on these portions. This is an example of Sterile Altica. We studied the Antarctic ice sheet surface elevation using altimeter data, and the surface height is classified at 200-meter interval for the winter season of 2013-14. Then all these parameters, whatever we are deriving, are useful for finally preparing the sea ice advisory, or you can say optimum voyage route, voyage route that is followed by the expeditors. So some of the parameters like sea ice concentration we have derived from OSCAT, then the iceberg positions we have derived from the RISAT, then the sea ice concentration using passive micro data also we have derived. Then we have monitored the sea ice condition around the Bharati using the optical data of MODIS. Then sea ice freeboard. This also we have evaluated using Sterile Altica data. So all this goes as an input for the preparation of the sea ice advisory. Now, study I'll like to share is that of um, this one algorithm we have developed at SAC, and it is basically using optical data, but eventually we have already started this work on SAR data also. We have developed automatic object-based classification algorithm for classifying the sea ice types, or you can say polarized features, and this is this is not a pixel-based approach, and this is the preliminary study that we did using the Landsat data. So as we can see that it is not just using the spectral properties, but it is also using the shape, texture, and context, and other, you can say, the spatial attributes to map the features. So and we can also use the other you can say features such as the shape and the position, and also the textural features as well. Then this algorithm we developed to classify the CI's features, and this is the final map that we have derived. So basically, we have segmented the image uh, in two different layers, and based on the size of the features. So if we have a larger area, then that feature will be classified at one level, and the smaller features will be classified at another finer scale level. So in these two levels, we classified the features, and we got the very good results using this particular method. But since it's not only about the technique, it is also about the operational monitoring. So that's why we'll be using the SAR data as well, and similar algorithm we are developing for the same purpose. Then so, this is about NISR mission that uh, this is a NASA and ISRO mission, joint mission, and the goal mainly is to make global measurements of the causes and consequences of land surface changes using advanced radar imaging. So, what is the concept is like NISR is the first satellite mission to collect the radar data in two microwave bandwidth regions, that is the L band and the S band, and we'll be measuring the changes with accuracy centimeters, and this allows the mission to observe a wide range of earth processes and also the cryosphere regions and earthquakes and volcanoes. So the radar actually, as I said, it penetrates through clouds and darkness. NISR will collect data in day and night in any weather, and also uh, it will have a repetitivity of 12 days. So it will be launched in 2000. It is planned basically to launch in 2022 from the Satish Dhawan Space Center in Kota, and this data will be freely available to the public, and, consistent with the long-standing NASA Earth Science Open Data policy. So I'll be discussing about the NISAT mission for the cryosphere. Basically, why this mission is important for cryosphere is the predicting the future of the sea ice level changes is difficult at present, and therefore this mission is very important for you can say will be very important for predicting the future of the sea level changes, because rising in the sea level will displace millions of people, and the adaptation will be very costly. So the recent observations also provide only isolated snapshots of ice sheet velocity and the respective changes. So, this mission will play an important part in that portion also. Further, the current satellite missions miss many of the most important fast-moving missions. So, fast-moving missions means they're having very high velocity. Then, uh, Also, the NISA mission will also provide a time history of ice sheet and glacial behavior. It will also play an important role to precisely measure the changing location near the coast. We say basically this is a grounding line technically. Then this understanding of ice sheet and glacier behavior and its corresponding changes will improve the projections of the impacts on sea level rise. And this will also help the planners of the mitigation strategies. So basically, I have more to discuss on certain portion. So, as I said that when we go for you say operational monitoring of the Antarctic regions, SAR plays an important role, and with the availability of Sentinel-1 data, you know, it has become really possible to derive the products at a higher resolution. So, what are the processing steps that are involved for processing the SAR data? Is first is the multi-looking. This is basically not necessary, but this is an optional step, and what it does is it basically transforms the data depending on the azimuth resolution and the number of loops basically. Then we go for calibration. So we convert the raw data to the sigma naught values or gamma naught values or beta naught values depending on what type of an application we are looking for. Then this calibrated data we give as an input for speckle filtering. So usually the SAR data is fraught with the problem of speckle noise. So we go for speckle filtering, and this usually will alter the values of the calibrated data. So we really have to be careful while we select this filter and window as well. Then we go for math correction, bandwidth. So if we are using the, we had discussed one algorithm where people have used polarization ratios and spectral gradients. So for that, we can create the as well using the HHHV or VV polarized images. Then later on, we can stack this and importantly, terrain correction. So terrain correction can be done using two ways. One is using the DM we can go for, or usually we call it as a drop. We call it as range Doppler algorithm, and another one is of geolocation grid. Using the geolocation grid, we can go for terrain correction. Then finally, we convert this linear values into the dB values, and later on, this process data we can use for the further analysis. So this is about the SAR data processing. I think I have almost covered all the portions, but if like I can, if you have doubts, you can ask. Hello, am I audible? Hello, 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 hello.
audible?
Hello? Sir, I think I somehow lost the connection.
Yeah, but you have logged in, showing you twice. So you log out from one and then
Oh, fine.
join again if possible.
Okay.
Hello. Now, Kavita ma'am, you are now connected.
Okay, sir. Am I audible?
Audible.
Okay. So I think I don't know where I lost the connection on which slide. So anybody can tell me so that I can just that slide.
Yeah,
So
it's you have started from first slide.
this is over. This was over. Hello. Was this over? Is the slides visible? Are the slides visible?
Yeah.
Visible, right? So can anybody tell me which slide from which slide I lost the connection? Because I was just speaking and later on I realized it. Signature
That is,
analysis of SAR data. All right. Okay, so that portion was over. So till all these slides, anybody has any questions or doubts, they can ask me now.
you can continue and we will have 5 or 10 minutes in the last of the session for question answer.
Oh, okay, fine.
Just make it full screen.
Yeah, I'm doing that. All right. So this is about the SAR data processing, and we did the signature analysis of sea ice and open ocean using Sentinel-1 SAR data, and this complete data set of from you say can say 2000 July 2018 to July 2020 we have processed the data, and obviously I'll show some other slide. So as you can see, it becomes very while we analyze the star data also we face a number of problems. Like you can see that this particular image of this is of Sentinel-1 process data, and this is of January 2019, and you can see there are certain portions basically an RGB image. But if you see the HH and HV separately, see this portion, this particular portion which is visible, it is visible in HH, but it is not visible in HV. And certain you can see some this textural pattern is seen. So what it is basically, this is not CIs also, and this is not any feature. It does not represent any feature. So now what it is? It is basically it can be due to because this is EW data, so extra wide swath data. So what happens is there are three beams, and the three beams data is stitched together to form one larger type. So this particular portion is effect of that. All right. And this portion also, like though we are saying that it can be a type of CIs, or you can say the NELAs, that is a new CIs formation, but it does not seem to be a feature. Then you can see this another image. This is of again general image, but this particular portion, you see this particular portion again it it is CIs, but what happens is it becomes very difficult to distinguish it from the you can say the smooth CIs. All right. So what this particular formation is, and it will eventually lead to a very completely different signature values, and it will converge with the you can say the open ocean values. So what is this? This is basically as the deformation of the fast ice is happening during December to February, it will follow this circulation path along the coast. All right, and most of these features are very thin, right? And that's why we'll be considering portion as CIs only, but with a concentration of 100%. All right, then there are like this feature. This is again January image only, but if you see this particular portion, this appears to us as if it is an open ocean, because as I said earlier, this blue portion represents the ocean and as well as the black portion. But it is not open ocean. It is an effect of you can say the winds. And what happens is the snow on the land ice due to the rifting process, it flows on to this ocean, and because of that it mixes with the open ocean signature. So we have to be very careful, and only considering the signatures, the backscatter signatures does not help, and that's why many algorithms came into existence which consider you can say other texture features as well, as I discussed earlier, like the textural features. Then they have also gone for like other ancillary layers as well, and with a combination of you can say people have fused the optical and the star data also, like with the existence of Sentinel-1 and Sentinel-2, the star and optical data. People have derived fusion algorithms also to deal with such problems. Then all this. This is a Mars image. You can see again. This is Sentinel-1 only. But what is happening is, if we see, we are comparing this with the optical images, because in optical images the open ocean will be clearly visible. Obviously, the sea ice and the formation won't be that much clearly distinguishable, but the open ocean will be clearly visible. So that's why we are considering, for the visual reference, we are considering the optical images. So you can see in the smart image certain kind of a formation, this circulation pattern is there. So what it is? So again, this is a new sea ice formation, and the signature of those newly formed sea ice has too much of similarity with the open ocean. All right, and that's why to deal with those, we go for the other spatial attributes and textural measures also, and also we go for polarized ratios. So then this image again, this is for May month, and you can see a lot of formations are happening in this month. So basically, this which is near to the land, this portion is basically fast ice. But what happens is, again, it has a very similar signature, brightness, backscatter signature with the sea ice. But this is fast ice. We cannot say this as a sea ice, and it does not play an important role while we derive the sea ice concentration. And then again, you can see the formation of the sea ice flows. So these particular patterns, you can see polygonal patterns, just like the pattern of rocks, you can see. So these portions, these are called as ice flows, and they expand into pancakes. But again, these portions have a very similar signature. It can have a similar signature to the sea ice or to the open water also, because when the melting happens, the sea ice which is accumulated over this sea ice, it will have a very similar signature with the open ocean, and that's why all these ambiguities arise. So basically, when the new sea ice portion, new ice formation is there, when the seasonal variation happens, at that time, it becomes very difficult to distinguish between the sea ice and the ocean using just backscatter. Then here comes the role of, you can say, the polarized ratios and the spatial attributes also. So here you can see we have got the you can say the graphical representations of these backscatter values, and what we did is we collected some certain samples. You can say we collected the samples of sea ice and the open ocean, and uh, of a 3 by 3 window. And from these samples, each sample we visually analyzed actually whether they are sea ice or open ocean, and the outliers were discarded, and the remaining, that is the pure sea ice and the open ocean, were compared, and the graphical representations were done. So if we see the HH image, then the threshold, that is of minus 31.5 to minus 20, it does not effectively classify the distinguish the ocean from the sea ice, because it has a similarity. When we go for polarized ratio, that is HV by HH, then it really helps to distinguish the ocean from the that image. All right. obviously there is a overlap of certain portion when we consider such thresholdings, but this particular signature analysis is very effective to know how the seasonal variations are happening, and also to we can say training the data sets. For training the data sets, the signature analysis is very important. So I think I am done with all the examples, and if people can ask me questions, so then I can deal with those.
Want to ask question, you may.
Otherwise, some certain questions I have some. Basically, I'll be showing you how what are the other data sets that are available on various websites. And it will be really useful also. So if people are having anybody is any sort are doing research or have taken projects in biosphere or any other cold regions area.
Queries from the participants.
Okay, fine. So, anybody is having the research study in Antarctic or any other Arctic, or you can say Himalayas, or anyone? No, nobody.
People
Okay,
are
okay, sir.